My name's Alex. I'm a medical statistician at CSM, the Centre for Statistics and Medicine at the University of Oxford, and this is my talk exploring the use of Bayesian techniques in a surgical trauma randomized controlled trial. The trial in question is this trial called Draft 2 that I've been analysing over the summer. Its full title is the Distal Radius Acute Fracture Fixation Trial 2. The distal radius is the kind of big bone in your forearm. And we're looking at broken wrists, just breaks that are near the hand. And the two different ways that we're thinking about testing for broken wrists are using a plaster cast, where you kind of hold the bones externally in place via a molded plaster cast, or these things called Kirschner wires, K-wires, which is when you make a small incision and then wrap the broken bones in a little wire to hold the bones in place internally. And then you kind of have a looser fitting cast on top. And we want to find out which one's better. The sample size is 500, and the primary outcomes, this patient-reported risk evaluation of PRWE, which is a score from 0 to 100, with 0 being fantastic risk function and 100 being complete terrible risk function. We've said the MCID, this minimum clinically important difference, which is kind of viewed as like a practice-changing difference, to be 6 points at the 12-month time point. We're randomizing 1-to-1, so 250 in the cast, 250 in the K-wire arms. We're only considering adults because children are made of rubber and they heal differently. And we're stratifying by age, less than 50 or greater than equals 50. The idea being that if you're less than 50, you're more at risk of, or you're more likely to be involved in kind of a high impact injury, like falling off a skateboard or doing something equally as daft. Whereas when you're older than 50, you've got bone brittleness, so you're more likely to break your wrist just by falling on it in like a low impact fall. Articular extension, which is kind of the way you break your wrist, you can either break it kind of top down from the hand or kind of across your arm, intra versus extra, and then center in hospital. And we're collecting data 0 months post-injury, so just after you've broken your wrist, 3 months, 6 months, and 12 months. And the interesting thing about this trial that I've been analysing, Draft 2, is that it's got a predecessor called Draft. So we'll play a game of spot the difference between Draft and Draft 2. So it's the same injury with a slightly reduced sample size of 461, same primary outcome, same randomization ratio, looking only at adults, same stratification factors. The only differences are that they collected baseline pre-injury rather than post-injury for Draft 2. And the two treatment arms, we still have the same K-wire arm with the little wire, but they compared that to a locking plate, which is when they had a kind of a more severe surgery where they held the bones in place with a big plate that was held in by screws. And the draft result was that there was no difference in the PRWE or actually any of the secondary outcomes either between K-wires and locking plate. Kind of the history of the draft trials is that if you can hold your bones in place with a lesser surgery compared to a major surgery, can you hold them in place without having any surgery compared to a lesser surgery? So there's an overlapping arm between Draft and Draft 2, the K-wire arm. And the question is, can we use the Draft 2 data, this trial that's really similar to my trial, Draft 2, can we use the Draft 1 data to contribute to the Draft 2 analysis? And the answer is yes. And how do we do that? Well, we use Bayesian statistics, and you probably could have guessed that from the title of my talk. I would say that because Draft 2 is still under analysis and kind of preparation for publication, I can't spoil the clinicians' fun and give away the true results. So I'm just going to present in this talk some made-up data about Draft 2. And I've kind of got 3 broad scenarios. I've got a no difference scenario, I've got a scenario where the cast arm is better, and I've got a scenario where the K-wire arm is better. All of the baseline post-injury, the PRW is very high, as you'd expect when you've just broken your wrist, you can't do anything with it, and that kind of improves gradually over time. The left-hand panel has no difference between the arms. The middle panel is cast arm is better, the orange line is lower, and the right-hand side is the K-wires are better. The model I've used for this analysis is just a linear mixed effects model. So I've assumed the YI is the PRWE for the eye participant, which has got a normal distribution with some parameters. And then this is the model that I've used. So I've adjusted for treatment effects, the time points, and then time point by treatment effect interactions. Age and extension are two stratification factors, and BI is a between person effect. We did play around with having a 2-level random effect with person within center, our last stratification factor, but we found that there was very little variation between the centers, so we decided to use this kind of reduced, simpler model. And BI has got a normal distribution with some parameters. And when you run this analysis, given our made up no difference data, in any kind of garden variety stats package, I've used R in this case. These are the outputs that we get. I'm not going to talk through all of them because it's quite boring and it's not really the purpose of this talk. But the one to look out for is just the top line, the 12-month cast effect. And you can see that the adjusted mean difference between the two arms is 0.28. So in a score between 0 and 100, that's a tiny difference. And the confidence interval is quite tight and comfortably straddles 0. So this is the kind of result you'd present in a publication. And this says that there's no difference between the two arms, which is kind of what you'd expect, given the data is actually made up to say that. And that's just our frequentist analysis. So switching to a Bayesian analysis, I'm going to start with a non-informative prior. This is almost more of a check than doing anything interesting. It's just kind of check that my Bayesian model is working correctly, because Bayesian analysis with a non-informative prior is effectively doing maximum likelihood estimation. So the results from this analysis should be very similar to the standard frequentist analysis. The non-informative priors I've used are just kind of off-the-shelf, very standard non-informative priors, with the parameters having normal distributions centered around 0, and then a precision, not a standard, not a variance, kind of 1 over the variance of 0.001 for all the BIs, the beta I's, and mu B. And then tau and tau B, again, are precisions, and they're done as gamma distributions. We use gamma distributions for variances and precisions because the gamma distribution, or the gamma function, is bounded from 0 to positive infinity, which is what you want when you're modeling variances. You don't want anything negative. So when we run this, I ran this in OpenBugs doing 200,000 iterations, and these are the results that I got. So I've suppressed all the other output, and I'm just going to focus on the 12-month cast effect. On the left-hand side, we've seen that's our frequentist estimate, and on the right-hand side is our non-informative Bayesian estimate. You can see that the adjusted mean difference has shifted slightly. It's gone from 0.28 to 0.08, and the credible interval has moved a little bit as well. It's credible interval now, not Bayesian, not composite interval, because we're in the Bayesian world. But the overall take-home message of both of these results is that they're the same, and that you'd give the same conclusion. So that's good. That kind of reassures me that I've done my my modeling right, and this is kind of what you'd expect. So what's an advantage of using a Bayesian analysis compared to a frequentist analysis if it just gives you the same answers? Well, one of the advantages is Bayesian inference. Because Bayesian gives you posterior densities that are true probability densities, you can then make direct probability statements about the parameters rather than have to kind of get into the murkiness of p-values and 0.05 and borderline significance and the difficulty of interpreting composite intervals. You can just use credible intervals, and you can make direct statements about your parameters of interest, just sampling straight from your distribution that you've created. And for me, I think that's a much more easily interpretable result for clinicians and also the public. So I'll just give you an example of one of these. So this is my 12-month cast effect posterior distribution for my no difference made up data set. You can see it's centered around 0, which is good, and looks vaguely normal. And we want to find the probability of there being this MCID, this minimum clinically important difference, a practice-changing difference, given the data that we've seen. So remember, the MCID we said was 6-point difference. So we find the probability of there being a treatment effect being less, greater than 6 or less than -6, because we don't mind which way the treatment effect goes. And then because this is a distribution, we can just sample and we can just find that probability distribution. And we find that to be 0.00015. Or we can flip that around the other way and say there's a 99.999% chance there's no practice-changing difference given our data, given my made-up data scenario, which is something that you could just put straight in a publication and would be a legitimate thing to say doing a Bayesian analysis, and I think is a very clear take-home message for the kind of main results of this this trial. And I've just done the same thing again for our other two data sets, the KY beta data on the left-hand side and the CAST beta on the right-hand side. You're probably just seeing the practice changing difference for the CAST beta data, for the KY beta data is 14%. So maybe like a risky, not sure you could claim that would be practice changing difference, whereas on the right-hand side, you definitely say that there's a 99.9% chance that you've seen the practice changing difference. So that's a very clear message there. Another advantage of using Bayesian analysis is the use of informative priors. So this is where the draft 1 data comes into my draft 2 analysis. So from the draft 1 data, I've managed to extract some informative priors. I've managed to get a 3, 6, and 12-month KY estimate for the PRWE, an age effect estimate and an articular extension effect estimate, and then also between person standard deviation, which is again is expressed as a precision, all of these using precisions. You can see that for the time point estimates 3, 6, and 12, I've truncated the prior from 0 to 100. This is because the PRWE only runs from 0 to 100. So it doesn't make sense to waste any probability mass outside of those, or probability density outside of those, that range. So that's why I've truncated them. Whereas for age and extension, I don't mind seeing a negative effect. There might be a negative effect. So I've set these to be unbounded normals. And then I've left all the other priors non-informative. And then when I've run this, again, using 200,000 draws from open bugs, these are my results. So the left-hand side you've seen already, that's the frequentis. The middle you've seen already, that's the Bayesian non-informative. And the right-hand side is the Bayesian informative. And again, the treatment effect adjusted mean difference has shifted a little bit. It's moved around, which is kind of what you'd expect for a informative prior, because we're actually giving it different data now and it's doing something else that's not maximum likelihood estimation. And the credible interval has shifted as well. And it has shrunk ever so slightly, but not loads, not as much as you'd expect it to shrink, given that we're giving it more information, which is interesting. It says that perhaps we're already set quite sure on our estimates. So there's not a whole lot more to kind of shrink it down, kind of regardless of how much historical information you put into it. So that kind of leads me on to the idea of using a reduced sample size. So what I did was, this is kind of like a throwaway at the end, like a very rough, something that needs a lot more work from me, but I think is really interesting. I randomly removed 100 participants from the draft 2 K-wire arm from my made-up data set to leave approximately 150 people left. I did this by resampling with replacement from the draft 2 data. This gives you a rough randomization ratio of about 5 to 3, so 250 in the CAST, 150 in the K-wire. And as I say, this definitely needs more further simulations and lots more random samples, and we need to really ascertain error rates and stuff like that, and requires a full simulation study to kind of get to the bottom of it. But I'll just show you provisionally what I've done. So on the left-hand side is our frequentis estimates for all 3 made-up data sets using the full sample size. In the middle is the frequentis estimates using the reduced sample size. So you can see 255 versus 150. And on the right-hand side is our Bayesian estimates using the reduced sample size and an informative prior. And I think this is a bit of a win for the Bayesians here, because on the left-hand side, all the results kind of go as you'd expect, showing a treatment effect where there is a treatment effect and not showing one where there isn't one. And the same for the right-hand side. Obviously, the parameter estimates are different because there's just different data being involved and it's different techniques. But the overall take-home message from each of these results is the same. However, in the middle, the frequentis estimate based on a reduced sample size for K-wire beta made-up data actually shows a null result when there should be a significantly different result. So that's kind of a big tick, provisionally a big tick for Bayesians, and a black mark against frequentis if we were to use a reduced sample size. So question is, was draft 2 too big? Well, very provisionally, I think yes. I think we get similar results using an informative prior and a Bayesian analysis compared to the full sample size using a frequentist analysis. So there's definitely an argument to be made there. A couple of questions still remain, however. So how much could the sample size be reduced by? I think that's a case for using the power prior, which kind of auto-calibrates how much weight to give to this historical data. And that's kind of how much data you could take away from the draft two trial. And one of the historical data and the trial data disagree. It's unlikely to happen for draft and draft 2 case because the trials are just so similar and the treatment arms are so similar, and it's run by the same team, and it's all the same trial effectively, answering the same research question. But there is a case that it might disagree. And if this work is to be more generalizable, that's definitely something that needs to be considered very strongly. And then just as a final throwaway thing, I'll just say that Bayesian probabilities are very, very good for prediction and prediction probabilities. So there's a case we made that you could use the 3 and 6 month data to try and predict the 12-month data, which would then try and predict the outcome of the trial. So if it looks like you're heading towards definitely having a null result or having significance one way or the other, then you can add an interim analysis to stop the trial even earlier. So you could even further reduce sample size, reducing research waste and money and saving money and doing all the good stuff, So that's my brief overview of kind of the power of Bayesian analysis in a phase 3 RCC in a real life setting. And I thank you, and I'll welcome any questions. And if you want to get in touch, my email's at the bottom. So thanks.
I guess to kick it off, I'll ask a question, which was, how do you actually get hold of? All right, okay. Thanks. How do you get hold of your prior? Did you just use the data and sort of eyeball it to cook up a prior, or did you go to experts as you would in sort of the subject?
No, so I used all the draft 1 data to ascertain the prior. So for the purpose of this talk, it's a rather provisional prior. It's definitely not set in stone. I think using the power prior would be the way to go to make a more kind of robust argument for it. So I got parameter estimates from the model using the draft 1 trial, and then kind of down-weighted it as I saw fit until I thought it looked suitably vague to accommodate having differences between draft and draft 2. But that's something that needs to be made more bulletproof for sure.
I guess I'll ask another one. So you basically use the data to form a prior. Do you think you could use the data from the earlier trial in a kind of joint model to help with prediction in the newer trial?
Yeah, well, that's kind of what the Bayesian analysis does very neatly, all as one big step. So rather than
is that what you did?
Yeah, that's how it works. Yeah, which is why I think Bayesian analysis is so great, because it all works so neatly and so nicely together. You don't have to worry about doing any complicated joint modeling or anything. It all clicks. It's nice.
So I've got a question now. If you don't have any historical data, could you talk through how you might set your own weekly informative priors, or I guess informative priors?
So if you don't, it depends very much on the setting. So if you're running a large trial where you don't have any problems recruiting, then I would just say use a non-informative prior. So use ones that OpenBugs or Stan or whoever suggests as being weekly informative or non-informative. Whereas if it's in a field where it's difficult to recruit, like a rare disease or something, then there's definitely a case to try and get expert opinion and there are tools that turn expert opinion into kind of mathematical priors that you can then use in your analysis. So it's very much dependent on the setting.
No more questions, I don't think. I guess I'll ask one more and then we'll go to the next speaker. So you stratified by age. Do you think it would be better to actually just put that in as a covariate, so the number that they are in years or even months?
Yeah, that's definitely a case to do.
Do you have that data or?
So there's an argument with RCTs that you analyze as you stratify, but there's also by discretizing, you kind of lose a lot of information. You lose some granularity. So some people, you have to stratify, you have to pick a point as a cutoff just to kind of put them in buckets, and then they analyze as a continuous variable. So you can do either, but I think using age as a continuous variable would probably be better in general.
So we have got one question through. So it's just about sensitivity to the choice. So how sensitive are your results to the choice of prior?
You'd be surprised that they're not super duper sensitive. It kind of depends on how much you downweight it, which is where using like a power prior would be quite useful, because then it downweights itself kind of automatically. But if you set a very informative prior, then it does make a big difference. But if you saw a plot of the prior that's informative that's making a big difference, then it's obvious that it's not a very useful prior. Whereas if you set a non-informative prior, then that kind of speaks for itself. I hope that's the question.
That's great. So we're having problems with Evo. His microphone isn't working. So we're actually going to go straight to Alessandro. So first of all, thanks to Alex. I don't know if you clap, but just say something nice in the chat. So we're going to go to Alessandro, who is from the Karolinska Institute, and he's going to talk to us about natural history models for breast cancer growth spread. So take it away.
So hi everyone, I'm Alessandro, and I'm really happy to be here to talk about some of our work on extending natural history growth model for breast cancer to future outcomes, and in particular to metastatic spread. This doesn't work. All right, I'll actually start with the take-home messages. First important message is that continuous growth model can be used to model the unobserved natural history of a tumor. And generally, these kind of models are more efficient than Markov and semi-Markov models, especially when including several factors at once in the analysis. Second point is that we introduce a model that relates the unobserved history of a tumor to the risk of future outcomes. And as I said before, we focus on distant metastatic spread. To the best of our knowledge, this is the first model of its kind in the area of breast cancer. And finally, just to state that it's really important to develop these new models, as we need this kind of relationship between the history of a tumor and the future outcomes in order to be able to assess new interventions and treatments, for instance, in a microsimulation framework. Having said that, let's get started. I'll start by actually introducing breast cancer. Breast cancer can be defined as abnormal cells in the breast that starts to grow and divide uncontrollably, and eventually forming a mass growth, that is the tumor. It is the most common cancer in the UK and is the most common cancer among women worldwide. Specifically, in 2018, there were 2.1 million cases of breast cancer worldwide, approximately 55,000 in the UK and 8,000 in Sweden. It's also the fifth most common cancer death in the world, with 630,000 deaths worldwide in 2018, and approximately 11,000 in the UK and 1,400 in Sweden. An important thing is that in most cases, breast cancer death is caused by metastases that are spread throughout the body. And that's sort of the lethal part of the breast cancer, essentially. Traditional statistical approaches to modeling tumor growth cancer data are continuous tumor progression models, either in the presence of screening or in the absence of screening, and multi-state Markov models, which have been traditionally developed with 3 states, such as no detectable cancer, preclinical cancer that is only detectable by screening, and then clinical symptomatic breast cancer. 5 states models have been proposed as well, in which case the preclinical and the clinical breast cancer stages have been divided into whether the lymph nodes have been affected or not, which leads to the aims of our work. The ultimate goal is to improve future outcomes. And by doing so, we need to be able to evaluate individualized screening, new treatments, intervention, and how any of this can be tailored to patients' characteristics. However, traditional prognostic models only make use of the information that is observed at the time of diagnosis, such as tumor size, detection mode, age, and so on. Therefore, our goal is to develop a model that relates the unobserved natural history of the tumor to the risk of future outcomes. Once again, here we focus on distant metastases. And this is important as we can see here, it's sort of a depiction of the natural history of tumors in breast cancer specifically. Here we have 4 hypothetical tumors, and not all of them are observed. For instance, only tumor B, C, and D are observed, where tumor B and tumor C are detected via screening, and tumor D grows so fast that it becomes symptomatic before screening. And on the other side, tumor A grows so slowly that it doesn't even grow to be detected over the lifetime of the tumor. And another thing that we can appreciate here is that tumors that are detected through screening have different characteristics compared to tumors that are detected symptomatically. And we can also see these differences in real data. For instance, this is real data from Sweden. And here we can see that tumors that are detected symptomatically have a larger size generally, which is what we saw also in this picture here. We see tumors grow much faster, so they get to larger sizes, while through screening, we generally get to identify tumors much earlier, which also improves outcomes in the end. So first we need to define a model for tumor growth, a continuous model for tumor growth. Here we assume that the volume at the tumor at time t grows exponentially from the volume of a single cell, that is V cell. We also assume that the inverse growth rates R follow a gamma distribution with shape parameters tau1 and rate parameter tau2. And this is to allow and also take into account the heterogeneity between tumors when it comes to the growth rate in the sense that we cannot assume a single growth rate for all the individuals as we've seen before. Each person can actually have a tumor that grows at its own rate. Excuse me. On top of the growth functions, we also assume that the probability of symptomatic detection depends linearly on the size of the tumor. And we also assume that screening sensitivity follows a logistic function of any set of covariates X that we can think of or that we measure. Once we define these models, we can formulate a likelihood function, and we can fit a model that brings all these components together using maximum likelihood and any general purpose optimizer, such as the optim function in R. This likelihood function has a closed form and is based on the distribution of tumor sizes as screen detection and the distribution of tumor sizes as symptomatic detection. Both quantities are conditional on screening history and relies on a variety of assumptions and approximations. However, we skip the maths for simplicity, as it would take a long time to actually go through it. But you can find more details in paper by previous PhD students in the group, Linda Abrahamson and Gabriel Seddon. What we want to do is to extend this model to also include future outcomes. And first, we talk about spread and what metastatic spread means. First, we have regional spread, that is when the breast cancer spreads to the lymph nodes, only to the lymph nodes. However, the tumor can also enter the bloodstream and reach other organs, such as the brain, bones, lungs, or the liver. And in this case, when the tumor expands to other organs, we talk about distant metastatic spread. And in general, when the breast cancer spreads to other distant organs, then prognosis is much worse. So what we do is we first define and formulate a model for successful distant metastatic seeding, which we assume to follow an homogeneous Poisson process with an intensity function lambda that depends on the number of times the cancer cells had divided and the rate of cell division. We include the exponent k with k greater than or equal to -1 to add additional flexibility to the model. We can estimate K from data, or we can fit it to a given value. And from this model is very convenient in the sense that we can identify a density and survival function that follows a viable distribution for survival times, which is nice. What we actually have to do, though, is to reformulate the model in terms of W, where W is the time from detection of the primary tumor, as we don't really know when the tumor originates, so we cannot model that. We need to model from diagnosis. And in order to do so, we just need to essentially rescale time. And once again, we can identify a survival function, a hazard function, and then a density function for this component of the model. And again, all of this follows a viable distribution, which is convenient. These models, however, relies on varieties of assumptions. For instance, we assume that it takes the individual specific time t0 for a metastasis to grow to a detectable size. We assume that metastatic spread is independent of the detection probability of the primary tumor. We assume that metastases grow into a detectable size before diagnosis of the primary tumor can be visible at diagnosis, but are not detected beforehand. We assume that metastatic seeding stops when the primary tumor is diagnosed. This specific assumption corresponds to a hypothetical treatment that is fully effective at removing not only the primary tumor, but also the possibility for all the cells and metastases that have been spread to further metastasize. This is a strong assumption, and we actually are thinking about relaxing this in future work. And finally, we rely on stable disease assumption, which means that we assume that the rate of birth in the population is constant, and the incident rate of the disease is constant as well, is stable. Once we formulate this model, we can again formulate a likelihood function. This likelihood function will first and foremost include a model for tumor growth and detection that was described before. Then we can also identify three kinds of observations that will contribute. We can identify observed events, that is, metastases that appear after diagnosis of the primary tumor, and this observation will contribute the density F. We can identify left-censored observations, that is, individuals with detected metastases at the time of diagnosis. These observations will contribute the probability of having one or more observed metastases, which is directly derived from the inhomogeneous Poisson process. And finally, we have right-censored observations, that is, individuals that do not develop metastases before the end of follow-up. And of course, these observations will contribute the survival probability S. Once we formulate all these observations, then we can fit the model again using any general purpose optimizer, as we can define a closed form likelihood. Here we illustrate this model in practice. We use data from CARES, a case control study with recruitment in Sweden between 1993 and 1995. From CARES, we extract 105 women with breast cancer detected symptomatically and with no screening history. This is because the model that we illustrated so far focuses on a scenario in which screening is not possible, or is not present, I should say. So we extract these 105 women with median tumor diameter at detection of 25 millimeters. Median follow-up was 5.67 years. And 45 women, or 43%, showed distant metastasis before the end of the study. Once we collect this data, we can fit the model. And what we can do is to predict the probability of being free of distant metastasis over time. That is, survival probability over time after diagnosis, which is which is interesting. For instance, we can see here some marginal predictions. So the marginal prediction for the model is the dashed line here. We also include a non-parametric estimator of the survival probability as a comparison, and we can see that our predictions fit the observed data quite well. We call these predictions marginals, as we average over the distribution of volume and growth rates. And of course, we can also get conditional predictions, which are maybe even more interesting. For instance, here we have predictions conditional on a given volume. So we have, say, 3 hypothetical women with cancer detected of different sizes. And we can see that we obtain 3 different, very different survival probabilities, actually. And we can see, as expected, that the blue line, that is large tumors, actually have worse prognosis. Okay. So what we have to do next, as I said, the model we described so far is only valid in the absence of screening. Therefore, we need to extend this to screening data, which is so the standard situation now. The likelihood function with screening data can be formulated as a conditional joint probability, the probability of tumor size and metastasis given model detection and screening history. We need, again, stable disease assumptions, and we use a procedure similar to that described in these 2 papers that I mentioned before to accommodate screening history. We actually have a paper that is almost ready, so we're almost done doing all of this, and we hope to have a preprint out soon that describes the full model. But the cool thing is that then we can, again, get predictions not only conditional on size, but also conditional on model detection, screening history, and all of that. And that's quite nice, I would say. Okay, so we're back at the conclusions, which is, again, what we said at the beginning. First take-home message is that continuous growth model can be used to model the unobserved natural history of a tumor, and that they are more efficient than Markov models when analyzing several factors at once. We know that we just introduced a model that relates the unobserved history of a tumor to the risk of future outcomes, and that, to the best of our knowledge, this is the first of its kind for breast cancer, at least. And finally, we want to acknowledge that this is fundamentally important as we want to be able to assess new interventions and treatments, and as I said before, for instance, in a microsimulation framework. That's all for me, and I'll be happy to take any question.
Okay, so if people just put questions in the chat, that would be great. I guess while we wait for any, I'll ask a quick one about, so you made quite a few assumptions about stable disease. How sort of robust are those assumptions? Mm-hmm. How robust is the model to deviations from those assumptions?
So regarding the stable disease assumptions have been shown in the past to be quite that is quite good to make those kind of assumptions. So there's not a large deviation from reality. Regarding the other assumptions, they are mostly sort of modeling and simplifying assumptions, which we, for most of them, actually, we aim to extend and to actually allow for more flexibility in the model. And as I described before, probably the most important one is to allow for, not a perfect treatment, which maybe doesn't exist. So, to allow that the tumor can sort of continue to metastasize even from the metastasis. So, we have some ideas on how to do that, and we will get around to relax all of that, essentially.
I guess another one would be, could you use this model, or how would you adapt it for other cancers? So you focused on breast cancer. There's lots of other cancers. Have you done?
Yeah. So So this is all focusing on breast cancer, and is based on loads of previous work in the area by the group. And I think in principle it can be extended to the other cancers, but you might have to reconsider the specific form of the models and the growth functions and all of these, as it fits observed data quite well for breast cancer, but you might want a different functional form, I don't know, for prostate cancer or something like that. So the way that you can go ahead to build these kind of models can extrapolate, but you might want to adapt it to essentially cancers that have a different biology than breast cancer, as all of this is meant to adapt to the specific biology of breast cancer.
I guess, could you just quickly talk a bit more about the metastatic seeding assumption, because you said that was quite strong and you wanted to do a little bit more about that. So where are you going to head with that?
So one idea that we have is that, as I said before, as of now, this model assumes that all the spread of the tumor can happen before diagnosis, and in this setting, you can interpret this as a treatment that we administer when a tumor is diagnosed that completely stops the tumor from further spreading. One thing that we could do is to have a parameter that we can also estimate from data, and that sort of allows for a fraction of the tumor to continue spreading, or for maybe like a reduced efficacy or spreading ability or this kind of thing. So you can include like chemotherapy or surgery effect and in the model and these kind of things. So ideally is rather than having a sharp cutoff, having a proportional cutoff or something like that. So this is our idea, and we haven't gotten around to do it yet, but that's the plan.
That's great, thank you.
Thanks.
So I don't think there are any more questions, and so that's the end of that sort of talk. So big thanks to Alessandro.